Yes. So one major announcement for students located in Skellefteå. So now I made my plans. So starting from next theory week, which is in 2 weeks from now, uh, or yeah, in 1 week actually, uh, I will be giving the class on Tuesday from Skellefteå. So I will come around, well, 9:30 in the morning. So I give a class and also I will take the assessments of the labs. So all Skellefteå students will assess in person to me. So all other students, so all distance students, so they follow the procedure as before. Also, so my slots for assessments to remote for remote students will be shifted to Tuesday afternoon. So this will be also reflected in the sign-up sheet. Is this clear? So do you have any questions? Okay. I will make a note on Discord also via Canvas about what I said. So let me share the screen now. Yes, so this thing we don't need for now. We need actually this. So do you see my screen? Can you confirm?
Yes, we see that.
Okay, very good. So I to make my and your life a little bit easier and more dynamic, so I prepared the notes in advance for this class, making some of the text printed again for easier digestion, so to say. So here is the agenda for today. I want to finish this ramping up module with introduction to machine learning and artificial neural networks with backpropagation algorithms. So if you have questions about the internals of backprop. So it's a good time to ask today. You also will work with these questions during Lab 1. So part 1 of Lab 1 is about the content of yesterday's class and partially of today's class. The idea again, so today I also will cover the adversarial attacks on artificial neural networks. In order to comprehend it or comprehend them and the theory behind them, so you need to know at least the minimum of functionality of artificial neural networks. So let's get started. And if you have any questions, so just write them in the chat so I see it in front of me, or ask enabling your microphone. So what did we talk about yesterday? So we started with introducing the problem of data-driven modeling. So we have a task of mapping an input that we observe through various sensory modalities. Again, so that's a very fancy word, but let's say we have images at hand, or we have collection of attributes describing certain phenomena. What it can be? It can be a table with salaries and all this employment information about different employees. It can be sound samples. It can be vibration sensors. So now go into purely technical domains like in um, e-maintenance and such. So in either case, so on the one hand, we have data collectively describing certain phenomena of interest. And on the other hand, we have a need to map this data to some desired output. And output could be I mean, what we can desire here. For example, we can ask to predict next possible instances of these variables that we observe. So that's a regression task. Or we want to do a classification task. So classification task, for example, well, in case of visual computer vision, so that's pretty much easy. So you want to characterize the artifacts depicted in the figure in the picture. But in general, classification could be a classification task could be for fault detection. So certain collection of sensory input um, is attributed to a specific fault or a normal operation of the object that we monitor. So in either case, so formally we have m categories, classes, and we want to map. We want to map the input, so which is this collection of variables, or now we talk in terms of features, and this collection of features also commonly referred to as feature vectors. So we have these feature vectors, and we want to map them into a score of a class. And mapping, so that's also not a very formal word, but also I mean, it's quite formal anyways. Mapping is done by functions. So mathematically, so we need a function that takes input and produces an output. Function in a very traditional definition, mathematical definition. The problem is, if you think about it, here we talk about multivariate function. So it's a rather complex function that produces just on say discrete values as the output. So analytically, I think it's infeasible. It's safe to say that it's infeasible to come up with such a kind of neat formula that do it for you for any given phenomena in the world. So what is left for us is a possibility to approximate this function. So if given that there is actually an underlying dependency between set of features and a specific category. So, and we want to approximate this function. And we do it by, again, pretty much extending a pretty much standard approach. So we model a category, so the dependent variable, so to say, by linear combination and applying certain function to a linear combination of the observed variables features. So that's a pretty much standard technique in math to do this kind of approximation. And here it is depicted on this slide. It is graphically depicted here on the top. Right. So we have certain function that will be activated by taking a linear combination of the features weighted by some weights from 1 to n. N is the dimensionality of your feature space. Okay, and here is the mathematical description of what I have said. And just for simplicity, I will skip the index act further on. And then, as I said, I mean, the underlying phenomena is complex. In what way it is complex? So that's kind of needs to be commented. So the easiest way to comprehend it is to try to try to kind of move yourself in this n-dimensional space. So to have the geometrical view on the modeling. So because as I said several times already, so this is an instance or a point or a vector in n-dimensional space. So in 3D space, it's easy to imagine, right? So I mean, so we live in 3D space. It's way more difficult to switch on imaginations on higher dimensionalities, like 10 or hundreds or thousands maybe, which is normal case for data-driven analysis. But if you happen to tune yourself to the wavelength of this high-dimensional space, so all these points, which is a description of describing particular phenomenon, so they form geometrical shapes. I will comment on this, Andreas. Yes, it's a good question. I started to comment already yesterday. But again, try to tune yourself on the wavelengths of this high-dimensional space and see phenomena as geometrical shapes. So, say, um, vibration measurements from passing, personal car, like a usual car, is definitely different from vibration measurements from measured from a passing by bus because it's heavier. So you see, and there's in this high dimensional space. So all measurements about cars will be kind of clustered in one space, and measurements about other vehicles will be clustered in other places. The problem is that in many cases, so these shapes they will overlap in a very, very complicated, sophisticated manner. And the task of the modeling, I mean, of these functions f, is actually to sort out all these overlapping cloud points in high dimensional space, such that you can decide mathematically by computing this function f, well, or a global f, uh, uh, just to map to a single number. And so that's why we need this cascaded structure. So to track all possible interactions, to build, fine grade borders between these shapes. So that's a very kind of hand-waving explanation of these Fs. So how many Fs you need? We talked about it yesterday, but that depends on the case at hand. For some simpler problems, say when the number of variables are not very high, the number of Fs and the hidden layers uh, uh, could be quite small. While for other phenomenons, for example, you take typical neural network for ImageNet. So you have many, many, many layers. So you have uh, many, many layers, and the width of the layers is very large. So, how to find an optimal configuration of a network empirically? So you run tons of experiments until you find the configuration that you need. So normally in the classification task, so the number of outputs always correspond to a number of classes, but all these Fs in between. You choose it as a result of optimization process. Uh, and this optimization process is empirical. So you really, there is no very kind of formally defined guidelines. So for this problem, so take n layers, and each layer should be that big. So there are some approximations. I mean, there is a theory you can find in the literature. But so let's just believe, maybe it's a good word, that this is a appropriate structure for doing this mapping from the input to the output. And apparently, there are theoretical papers, maybe not relevant to kind of give you for reading in this course, but which the works which formally proved that in this very shape, so this construct, which is called artificial neural networks, feed-forward artificial neural networks, is a universal approximator of function. So it can approximate any function. So that's a very powerful construct. So now, in a fast-forward manner, so I will fill in the gaps, saying what these Fs are, and again reminding you about the general principle of training. But are we good so far with respect to understanding these basic building blocks? Okay, no protests. Good. So to do that, I again, I want to uh, attempt to create an analytic form of the equation of this function just for a single branch and maybe even a single set of weights. So, and that's what I try to depict here. So what we have here, so we have the output, which is a function of weighted results of functions of all the layers down to the input with different set of weights, which are randomly initialized in the beginning. And these are the weights that will be tuned. And now I finished yesterday with information that, okay, so given this formulation, so what we want essentially, we want to correct errors. So obviously, if the weights are chosen suboptimally, so the scores, they will be pretty much random guess. And but we are talking about supervised learning, meaning that we know the truth, we know the desired outcome of this system, and we want to fine-tune this weight. So we want to choose the weights such that the output actually corresponds to the desired one, to the truth, which is called ground truth. And to do that, again, we need a mathematical construct and a mathematical construct that measures an error, classification error, the mismatch between the score and the truth. And this is done by yet another function. So we have neural network itself as a function, a global approximator of any function. And we need a loss function, a function that measures error between the computed score by the neural network and the desired output. And yesterday we talked about the ground principles for training neural networks, which is computing gradients. So evaluating how evaluating the trend of the output score, so the functionality of the neural network, um, by change depending on the change in the weights. So you try to change the weights a little bit here and there and such, and you want to see a trend in the output score. And basically, so taking these partial derivatives at the end, it's core of this optimization process. So we want to minimize the loss. So minimize. So we want to minimize the error. So that should be understandable. And so these partial derivatives of this function with respect to each weight down to the input actually are called gradients. And so this whole thing is a vector of gradients. And what you do, so the learning itself or fine-tuning, again, so you should see it as optimization, or it's a fine-tuning the parameters of this approximation function. So you take the old weights and you create a new one, you compute a new one by taking the opposite trend. So this partial derivative is a trend, and you take the opposite direction. And then again, so that's part of the optimization procedure. So you shouldn't take the very drastic steps in the optimization process, so to not to overshoot this minimum that you are searching for. All right. Um, so now, very quickly, putting some meat on the bones, so to say, what is this f? So we need a function that somehow restricts the result of this of the computation um, of this linear combination of inputs. Why is that so? Well, simply again, to be mathematically be within the constraints, the optimization constraints. So that's important. And for this, we need a nonlinear function. Nonlinear means nonlinear and bounded. So you want we want to keep the values of the weights within certain bounds. And there are different options we can use here. So these are the usual suspects that you can find in the context of backpropagation. So the functions which are called sigmoid, hyperbolic tangents, and a rectified linear unit. So here on the in the middle, you see their graphical shape. So, and the bounds. So sigmoid, for example, is a function bounded between 0 and 1 for all x's. And here is the formal definition of a sigmoid, well, hyperbolic tangents and a ReLU. And when introducing these functions, it's very interesting to or I mean, you must eventually compute the derivative of this function with respect to the inputs, uh, right? And with respect to if you take the derivatives, so you can verify it, that the derivative can be expressed as a function itself, as a sigmoid function itself, for example. So here, or the tangents function itself. And this is a very useful property because when computing the activations on a forward path, so you input the values and then you start to compute all these functions sequentially, one after another. So you immediately can compute the derivative with respect to input. That's very neat. So the computation of derivatives, which is done. Oh yes, sure, of course. I mean, you could. I can be slower a little bit, but if you let's do like this. So tell me. I mean, the moment that probably you want some more clarification, and from there I will take it piano, or maybe I just take a slower pace in general. Uh, yeah.
Mhm.
Yes, but the thing is that well, this topic is really a prerequisite. So we, for what I want to tell next, So maybe I can suggest that you uh, watch it, well, obviously, offline, plus read the suggested material that I posted yesterday in Canvas. But so let me just continue and maybe in, yes, Joachim.
Uh, do you hear me well?
Now, yes.
Great. Can you maybe post before a lecture what we can read up on to be more up to date on what
That
you're going to teach?
that
So,
was that's what I did yesterday.
okay, yeah, I didn't quite understand that, but then I know. Thank you.
So all the information needed is posted, including the today's slides.
Yeah, do it also point to that this is specifically good to read before this lecture, or have you just posted it according to the study theory?
Yeah, I mean, I think all the information for the module should be read, kind of,
Okay, yeah, of course, but I think it would
when
be also,
available.
yeah, of course, but I thought the specific information can help us understand your lecture, for example.
Sure, sure, sure. But again, so you see, I have to admit, so this is a very specific program you learn, and as I mentioned in the beginning, I know you have very mixed backgrounds. I'm not sure that the majority had this prerequisite on backprop algorithms. However, so that's not the point with this class. So you need to keep
I
up a little.
understand that.
But I will try to. If you have some specific questions, like okay, now I'm lost, so stop me so I can take it.
Yeah, of
But
course. Thank you.
but I deliberately want to finish this up in a rather fast forward manner. So let's see how it goes. But again, I'm open to all questions, so we can take it. Um, yeah. So what I'm saying is that this figure that you see on your screen is still very abstract. So it kind of denotes the general idea of creating a universal approximator of a function that maps input to output to this course. And now I'm saying that, so we defined the optimization process as minimization of the cost function, so which will take the outputs as one input, the ground truth as another input, and compute the error, the mismatch between the two. And if you have this function, so this is a function, and normally, so looking a little bit ahead, so this is a continuous function and differentiable function. So you can take a derivative. So you can take a derivative, and by doing this, you enable the optimization process or minimization. So you want to minimize the error. That what was the idea described here. So you need this new function. But again, so when we define it, so we need to take the derivatives, and to take the derivatives with respect to weights, we need to know the details, what these functions f are, right? And the options you have, they are not that many. So these pretty much are most of the standard functions. And as I said, so the type of these functions is chosen by the demands of the optimization, by the demands of the problem for optimizing a function. So that's, I mean, maybe to fully comprehend it, so you need to renew your math classes. And now I said also that computationally, so despite the fact that it kind of looks complex, so and the derivative should be kind of complex. So the if you do all the steps taking a derivative with respect to x, You end up with a very computationally simple equation. So when computing the activation function on the forward path, so when you compute the scores, so you immediately compute the derivatives. So computationally, so you prepare it for the optimization for solving the optimization process, optimization task. Um, so the next, the last two very important pieces in this recipe is the shape of the output block of neural networks. So what I talked so far ended somewhere here. So let me see if I can. So here is the border. So that's I talked. So previously, I will not. Well, I will just dash it. So we talked before. So far, all right. So if you think about it, so now the result of the output of our neural network, as I said, is a score. So if we have for each class, so if we have m classes, what neural network spits out are numbers. Say score for class 1 is 0.49, for class 2 0.112, etc., etc. So just set of numbers. And now we are about to choose this error function. So how to go about it? So in principle, there can be many choices for choosing the loss function. I have already mentioned the main property of it is that it should be differentiable and convex, so that that there are pronounced minima which you can find. We will focus on one specific function which is called cross entropy, which is widely used in many cases, like almost by default. Whenever you see a neural network architecture, so and configuration of the last layer, so you see this cross entropy function as a as loss function. But what is it about? For starters, so let me just maybe skip a couple of slides. Not that one, so I have a textual one. Yes. For starters, cross entropy. Oh, sorry. So it's not very responsive to my gestures. Okay, you can read it online, but nevertheless. Cross entropy is a function which is a measure between two distributions. So probability distributions. And on the one hand, we have a probability distribution, we should have a probability distribution of the predictions, so which are called PI. And on the other hand, we should have a probability distribution of our classes, which are CI. And so the function itself, it looks like this. So I will not go into it. So it's also sometimes also you can find a term negative log likelihood, so which is same thing. But nevertheless, so this is our error function, so which takes the probability distributions of the predictions and compare it to the probability distributions of true outcomes. But this scores, so that's what I want to very quickly come to. These scores over here, these are not probabilities. So these are just numbers computed by disactivation functions, and well, they can take arbitrary values and they do not sum up to one at all. So what we need to make this output compatible with this cross entropy cost function. I will now comment on the two questions in the chat. So let me just finish what I want to say. So you need a function that takes this course as an input and make them look like probabilities so that the output sums up to 1. And there is such a function which is called softmax, again, on the level of definition. So if you kind of want to really get into machine learning, what you need to do, you basically take any term that you don't understand and go deeper and read about them. So all this information is exists in the source that I posted yesterday, and in all other sources. You can even use ChatGPT. It's very accurate on just this part of the theory. So now I want to go back to questions in the chat. How do we know the actual value of the ground truth, which we compare to the calculated score? That's a good question. So that's part of your training procedure. So what you, so the principle here, so let me just go back to this one. So you will, as I said, so you will train this network. So basically you will fine tune the weights sequentially. One, so you're taking one sample from your data set at a time. So what does it mean? So you have a data set. Say, for example, you will work in your lab with the data set called MNIST. So it's a data set of handwritten digits. So 28 by 28 pixels digits. And so in the data set, so you have this 28 by 28 pixel intensities, and also a label for so each row is the data itself and the label, and that's what you do for the training. So you take again, so now this is a very simplistic regime of training and very inefficient rather. So you take one sample at a time. So you put the data here, and based on this data, so the score will be computed, and you take the label. From this data set for this sample, and you input it here. So what I omitted here a little bit, how you encode this label. So the label, for example, 7 should be represented in the format compatible with the output of the network, which means that it should be represented as a vector of size m, which is which is the number of classes you have. So what you do for encoding, so you take a vector of size. So for example, in MNIST data set, it is of size 10 from 0 to 9. So you have 10 values in this vector. And then you put 1 in the position of the label. So if you want to encode 7, label 7, so you put 1 in the 7th position of the vector. And then the score vector, so the format of the score vector becomes compatible with the format of the target label. And this type of encoding, by the way, is called one-hot encoding. So you have all zeros but one, which is the label. And as I said again, so practically you don't do training sample by sample because that's a really inefficient way for large data sets. What you normally do, you do something which is called batch training. So you take several you take several uh, samples at a time, say hundreds or 100 samples and 100 labels, and you do computations. You do matrix-based computations. So you parallelize computation, but the principle is pretty much same. Yes, that's what I say. We are in the supervised learning. Yes, of course. So that what I say makes only sense in the supervised context. So in this course, we are not concerned with unsupervised. So by default, you can think about supervised learning. So now a question from Mohammed: Is this the, so first question of Mohammed? Uh, uh, is this for an error gradient or gradients in general? Well, I think it's a kind of tautological question. I mean, here we take a derivative of loss function, which is a error, which is an error function. So it is a gradient of error function. Now which is obviously a part of general principle of computing gradients for a general function. So how important is to be able to list every function? All of this builds upon rather than understanding of the concept. Well, that is an overview level, believe me. So that's the bare minimum you have to have in mind, and you will deal with it in Lab 1. So we don't go deep into theory here, not at all. But of course, I mean, for understanding attacks that I will show you in the second half, so that's, I mean, of course, you can boil down to some, so you can ignore some details. But here again, I'm just saying you what the meaning of each function is. So and the meaning of, for example, softmax is just to make the output of scores be compatible with the choice of cross entropy function that we choose to be a loss function. So, and I will not go into, so you can have a look at all this information that I will supply to you. I want to finish this introduction by this last slide, which actually put all the pieces together. So this is our neural network, so the hidden layers that map the inputs to scores. Then we normalize the scores so that the values that you have here after this softmax box, they actually sum up to 1. So that's a normalization step. And become compatible with a cross entropy function, which basically compute an error between the outputs here and our one-hot encoded labels. And so what it does, so what we do actually as part of the backpropagation training, so we take the derivative of this function with respect, well, at the end we want to take a derivative with respect to weights. And we do it by, so this on this slide I show just the very first step of computing the derivative through this softmax function. And the idea here and the idea behind the entire backpropagation algorithm is that you use the chain rule for taking derivatives. So for taking the derivative of the cross entropy function, which is h, with respect to the scores, so you need to take the derivative uh, of the um, of the function with respect to the softmax output and multiply it with the derivative of the softmax with respect to the scores. So that's a chain rule. The good news is that so there are simple well the final results of taking these derivatives. So for your information, you can find some uh, calculations even in these notes. Uh, but the derivative boils down to very simple computationally simple equations, and that's what you will see in this sample implementation of artificial neural network that you will work with during Lab 1. So this stuff over here, which is basically the result of the softmax calculation, and CI is the true label. So this simple difference is not an error. It's a gradient. It's a gradient of a cross entropy function with respect to softmax and the scores. But you will get some more insights during Lab 1 when performing Lab 1. Any questions on this part? So we can take a couple of minutes break so you can even enable your microphone if you have questions to ask verbally. So we resume in exactly 2 minutes or 3 minutes, 11:05. Do here. So here it is now when we are familiar with this backpropagation of neural networks. So now we actually turn into the security aspects of it. So what does it mean making a neural networks secure, or what makes them vulnerable in a way? So the information that you have to read is well, generally you can find it in the papers. So, but at the end of the presentation, so let me just um, go to the very last page over here. So here's the suggested reading. So that's a paper you must read for sure. So the other papers, so they touch on different aspects of what I will be talking today, or whatever part I managed to cover. So, and I put PDFs right out after the class, so you can read them all. Yeah. So we are talking about adversarial attacks, malicious attacks on machine learning in general. And our focus is artificial neural networks, as I have presented before. So let's talk about the threat models and the taxonomy of attacks. We can differentiate white box attacks, gray box, and black box attacks. So today we focus on white box attacks, and next theory module we will be talking about black box attacks. So what is the difference between them is the kind of information which is available to an attacker. So white box attacks, obviously, an attacker has full access to the model. So it has access to all the weights, parameters, gradients, so the configuration of the network. And that's what we'll be focusing today. In the black box attacks, you treat the neural network as a black box, well, as the name suggests. Um, there are different types of attacks. We will cover some of them, or we will cover a general principle. So amongst the most important ones are evasion attacks. So and that's what we'll be doing today. We're looking at today. So we have adversarial examples, which are crafted in such a way that the network produces misclassified results. And there are other types of attacks, as you can see here. A special class of attacks I will comment later on is about physical world attacks. So when knowing the functionality of the underlying model, so you do not uh, mess around with the data. So how the data should be modified. So all previous attacks is about actually interfering with the way how data is input to the neural network. Physical world attacks is about adding artifacts to the real objects, and so that the network produces wrong outputs. So we will be focusing on a case of computer vision, so just for better intuition. But what I'm saying is applicable to a general class of modalities. So, for example, speech-to-text recognition. So you add certain modifications to the input, and then it starts to produce wrong results. And by the way, so these slides are available in Canvas, so you can download PDF and follow it on a side, not only from the screen. So yes, any question or something? No. So I see, Amir, you enabled your mic. You have a question or something? No. Good. So what we will be doing today, we will be focusing on these two, fast gradient sign method and projected gradient descent attacks. One pixel attack is for a self-study, so the article exists since a long time ago, so you probably have looked at it already. And I will make the connections between the two today. So also, by the end of the lecture, I will post a sample implementations of this attack so that you can study offline. So, what is the idea? So what we covered so far, is the really high-level view, abstract view on what a neural network do with respect to mapping input to output to the classification. So this is our bird view architecture. So we have input, we have so this lines. These are the linear combinations with weights. So these circles are activations, our nonlinear functions. And so here we have our loss, so cross entropy, for example, and so which takes the output and truth and computes the gradient of error, of this error function. And these gradients are used to basically tune the weights over here. So how can we perform an attack? So what does it mean in here? So what do we want to modify here so that so that given certain input, and I think the next slide will be misleading a little bit. So that the output is erroneous, so that so the very well trained network start to produce wrong results, wrong outputs. So what are the perturbations? So what do we want to perturb? We want to modify the input such that and that's I'm sorry for that. So I want to do one quick modification. So here. So now. So what we want to do, we want to modify the input so that the so we want to add something to the input so that the result of the computation on the forward part. So we don't retrain the network. So that's what we want to modify. Produces wrong results. And we want to modify the input such that it won't be visible or minimally visible to the outside observer. So we have a question, please.
Yeah. The input is sample of the data.
Say again.
The input is a sample of the
Yes.
data, right?
Yes.
But how can we modify that? Shouldn't we modify the weight instead?
No. I mean, you should wait a little bit.
Okay.
I'm coming to it. So you modify the input. You do not modify the weights. Weights are static. I mean, but the attacker. So here we assume that the model is available for the attacker. But the production models, so in the model in production, so that does something useful. For example, it sits inside a car and monitors the signs or whatever you do object detection. So that is owned by the producer. So you don't mess with it. See, so that's the point. So, but you can craft you can craft the input. Uh, and again, you should craft it in such a way that I mean, hopefully it won't be visible for the observer, so that the observer cannot say that okay, so that's something is seriously wrong with it. And here we come to this definition of norm-bounded perturbations. So. Right. So basically, we want to control a property of the input such that satisfies certain mathematical property that basically put in formal way. So it is norm bounded. So you bound, so you do the perturbation such that the norm of your module modification is within certain bounds. And there are so the notion of norm is directly linked to the notion of distances that we talked about yesterday. Yes, perturbation is an attack, yes. 。 Um, yes. Norms. So we want to characterize the, or we want that the norm of the attacked input is within certain bounds. And there are different types of norms that we can use. So similar to different distances that we discussed yesterday. So for example, L2 norm, so the Euclidean norm. So this is the distance, you can think of it as a distance of a vector to itself. It is described with this formula. L infinity norm, so that corresponds to this Minkowski distance where p is infinity. So basically, well, in simple words, it boils down to finding the maximum value of components. So being equipped with this norm, so we what is that? There is also Manhattan norm, but we won't be doing with it. Doing it. So what we want to do, we want to craft an input. So if we have if our original input is, for example, 7, so we have access to the original inputs. So we want to modify it, so changing intensity of pixels in certain positions, say 518 to some new value, and probably you do it in several places. Here, there, and there. So just modifying the color of these pixels to shades of gray, for example, so that when you input it, so visually it's pretty much same symbol. So the pre-trained network start to produce wrong outputs, and mathematically it is expressed here. Find such an adversarial example X by adding perturbation delta, that when you input it to your neural network F, so that's our global approximator, it produces wrong output. So the output is not equal to the target label. Yes, please, Joachim.
Yeah, just so I understand it correctly, basically you have the training data, which you add noise to, and you use the algorithm to make the noise pretty much unnoticeable, so the training data looks the same, but it isn't the same.
Okay, so again, good question on the terminology, on sorting out terminology. So the word, so first I want to comment on this term training. So training testing makes sense for the optimization, so for the training of artificial neural networks. So you want to create a model. So for this, you have a training test, you have a test set. Okay. When training is done, meaning that you are satisfied with the performance, so you minimized your cost function. So all your, first of all, all your test cases, so you have also a validation set. So a separate set on which you kind of pre-check the quality of your neural network. So when you're satisfied with the performance of your neural network, so there is no more training or testing. So you want to deploy it in your system. From now on, whatever you input is, well, you can call it a test, but it's kind of just input samples that your network takes and produces the result. Is it clear? So what we want to create new examples that look like legitimate ones, but produce wrong classification. Is this clear?
Yes, very clear. Thank you.
So let's talk about these two methods again in a very fast forward manner, just to understand the workings of it. So these two are fast gradient signed methods and projected gradient descent. So there is more information on the slide, so you can introduce in some extra arguments. But let's focus on the functionality of each attack. So the idea is that we assume that our model parameters, gradients, are available for crafting this new examples. And of course, as such, we also have an access to the data which was on which this network was trained on. So roughly speaking, so we can at least guess so the data that it was trained on. And what we will do, so we will input one example, see how it's classified, and then we will figure out what the distortion should be added to the input so that the classification is changing. So and here is the mathematical formulation again. So you have the original input, the true labels, our neural network, the loss function, so cross entropy. And so this will be our perturbation. So the FGSM method is about observing the gradients for a valid input and the target label. So backtracking it to all the way to the input through all the hidden layers and inverting the sign. So you basically add the trend. So for which the network was optimized to the sample. So you make the opposite trend, so that the network makes an error. Do we use our creativity? No, you don't use your creativity. Not at all. I mean, you don't have enough creativity to come up with such examples. You must understand what is going on. I mean, all the attack. Yeah, well, at the end, that boils down to changing color, the uh, and other features of the image, yes, but you cannot do it by kind of manual crafting. Maybe, I mean, you will succeed, but I mean that would be totally suboptimal, especially for large-scale neural networks. Okay, so you need to base your attacks on mathematical principles behind the networks and any other machine learning algorithm so that you succeed. Okay, so this is the attack. And at the end, as I said, so when you add this perturbation, so you will see it will change some colors. If we talk about computer vision applications. So what we do, so step by step. So for each sample, for the sample that you want to alter, so you compute the loss. So again, so you have the model at hand. You compute the loss and the gradients. And then you extract you extract these gradients. You take the sign, and you add a small perturbation to the sign, so making the input appear as an opposite trend. So let me skip it. And you do it in one shot. So you just so take an example, monitor well, do forward computation, backward computation, and apply the changes. That's I mean, one way of doing that. There were further modifications of this attack, which actually become more sophisticated in a way that it introduced a, optimization process into the crafting of this perturbation, such that based on mathematical properties, it becomes imperceivable by the outside observer. And one of these methods, I will show you on the demo very, very shortly. So it is a projected gradient descent. So the fundamental, I mean, it's a next step after the FGSM method, where you just do it in one shot. In the projected gradient descent, you define crafting of adversarial examples as optimization process. So you take this sign of the gradients what you do, you actually do several iterations, choosing such perturbation to the image that minimizes this norm of the malicious input, so that the changes become barely visible or pretty much invisible at all. And this is done by iterative process. So you want to, on the one hand, you want to maximize the effect, the bad effect from your perturbed input, but then you want to keep it within the bounds of the norm. And in this case, the just norm was infinity norm. So, which again, in simple term, means that you restrict your changes in the input to be within certain range. So that if any coordinate overshoot the predefined range, this is the norm. So you just bring it back to this border value. And this is described by this mathematical equation. The model doesn't, no, Daniel, the model doesn't learn new patterns. So a model is fixed. Imperceivables, it means that when you look at a modified image, you don't see changes. Well, you or a computer program. So comparing the two images. I mean, it depends what you mean by hidden. So no, the changes are not hidden. Changes are introduced to the input, so they are not observable. That's a different thing.
So they basically look like the normal input that can't be perceived by the eye, for example.
For example, by eye. Maybe I can, just to be, again, you can read this theory in peace and quiet. I can show you this thing. So let me just download. So um, so let's take this example. So I just took a random picture from the internet. So and again, I don't I don't know the type of the animal. I just assume that it's what is it, leopard or something. And what I did, I created an example that takes this input and perform an attack. So the attack itself, so let me see. So this is a class, the attack. So when it is called, so it will take the image that I supply and true label, true label of it, and pass it through well, publicly available model, which is ImageNet, so you can download it from the internet. And what it does, it pass the image through the model, so and record the outputs. So these are the scores, and so compute the gradients, compute the loss, not the gradients, the loss so far. So it takes the outputs and compare with the true label. So that's exactly what I described previously. And then it computes again. So the model is at hand, so you can compute it on the backward path. And so when computing, so you record the gradients, gradients, so all the way down to the input, and you take these gradients. So and this is important. You don't modify the weight, so you don't retrain the network. No, the network is fixed. Daniel, so that's a very important. I think if you will watch this recording in the first part of it, I said implicitly, and that is super duper important. The loss is not output minus input, not at all. The loss is cross entropy. So and the cross entropy has the sophisticated probabilistic definition. The gradient, when it is computed with respect to softmax, boils down to output minus true label. So, but that's why I said that it is important to at least have, this bird view understanding of nuts and bolts, mathematical nuts and bolts of neural networks. On the level of, at least on the level of terms. Watch it in a slow pace and try to get it for you. But what is happening here in these few lines? So implementationally now with all these frameworks, it becomes rather simple to program the neural networks and train them. In this implementation is based on the Torch library, and the model is downloaded from the internet. I will show you this part of the code, so you can also explore it offline. But what you do, as I said, so you pass the input in this very few line. What you see here, you pass the input, you collect the outputs, so and you compare it using the cross entropy function with the label, the target label, and you start computing the gradient for this input. So that you do with this function. So, and this gradient is computed all the way down, through all the hidden layers down to the first input layer. You take it. So you take the sign of this gradient on the first level. So when you take input and you multiplied it with the weights, and you input it to the first layer of the neural network, and you multiply it with the epsilon as a small noise, and this multiplication actually means the opposite trend. So when you adding it to the legitimate example, so it makes the network behaves differently, right? And okay, so you can see, for example, different parts of how images um, how images retrieve or downloaded, and so the ImageNet network is loaded. Or sorry, not ImageNet, sorry, ResNet. I should have been more precise. So you you input it from the public libraries. So after this line, your model is the pre-trained neural network, pre-trained on lots of classes. Okay. Yeah, but what I want to show, I want to show the final result, just to be demonstrated on the on this image. So that was the original one, and I need adversarial example FGSM. Uh, adversarial image. So this is the image that was created in one pass, crafted in one pass, such that it is classified wrongly. So you could check yourself. So originally it was classified as um, leopard, if I'm not mistaken. And then the final answer is the final answer was what was it? Egyptian cat or something. But the label has changed. And just commenting to what coming back to what Mohammed has written is that um, so you see, I mean, the artifacts that have changed are well, colors, if you wish, but well, intensity of different colors. So that's the point. But again, so I hope I understand this comment correctly. That is the whole thing. I mean, we create an algorithm that that figures out what are these minimal changes. I hope you bear with me here. Um, so if we now look at this PGD, projected gradient descent. So I have the same similar script for PGD, and yeah. So let me see. So in the PGD case, so the attack is slightly more complex because so now we have a loop, so it will be an optimization process. So it does pretty much same as the FGSM, but in several iterations, minimizing these disturbances. And if I show you the final result of this run, so for example, PGD adversarial, yeah. So this this is an adversarial example which produces wrong outputs with PGD. So if you compare it with this one, so where, oh, sorry, it's an original image. Adversarial image. So you see, uh, on the PGD, so the changes are they are not even visible with naked eye. So we managed to change the intensity of pixels in in a minimal way through this iterative optimization process. And I can also complete. So now we have 2 minutes to go with two messages. First, you in the supplied PDF of the lectures, you will see also the information about the defenses. So the defenses is about actually observation of these attacks led to defense mechanisms. So that knowing that images can be crafted, so there are different ways. You can train the network by generating adversarial examples, for example. Or when you can train a network assuming the certain bounds on the variation in the weights, so that or you can do pre-processing of images before inputting it to basically restrict the modification or remove the effect of modifications. All these defense strategies principles are overused in the rest of slides. And also, so please have a look at the papers if you want to know the details. But what is needed for you, the compulsory part, is to understand the main principles behind FGSM, the attacks themselves, and PGD, obviously, as well as the one pixel attack. So again, the one pixel attack you will learn through the paper, which was linked for many days now. And the idea is that, compare it to PGD and FGSM, you don't modify many pixels or many inputs, but a single one. So apparently, you can conduct an attack by modification of a single input. And that's really powerful observation. So, and that's what you will work with in the lab. So, any questions on this topic? Then all the material which is needed for preparing you for the quiz will be available as of now. Well, now I will load the rest of the articles. Otherwise, everything is already there. So if you have questions, so you can ask in Zoom. Sorry, in Discord. All right. If there are no more questions, then thank you for today. So let me stop the recording. And see you next time. I will meet you during assessments as well as during the next theory module where we will go deeper into black box attacks and anonymization, obfuscation, and deployment of neural networks on untrusted platforms. For that, again, you have to get better understanding of the internals of neural networks, at least on some superficial level that I have presented. Okay, thank you all. Bye-bye.
Thank you.